Thanks everyone for joining the Temporal Graph Learning Reading Group today. We are very excited to have Yixu from Shanghai Jiao Tong University today. He will be talking about his Triple AI 2023 work, Temporal Knowledge Graph Reasoning with Historical Contrastive Learning for us today. And Yixu is a third-year PhD candidate at Shanghai Jiao Tong University under the supervision of Professor Luo Yifu and Professor Xinbing Wang. His research interests include natural language processing, knowledge graphs, and data mining. Specifically, he is devoted to the research of large language models and temporal knowledge graph. And so I will hand the mic to you, Yixu.
Okay. Hello, everyone. Thank you for your inviting me to this reading group. It's a great honor to share my work here. My name is Yixu, PhD candidate at Shanghai Jiao Tong University. Today, I'm presenting our work, Temporal Knowledge Graph Reasoning with Historical Contrastive Learning. First, please allow me to introduce our laboratory and its products, SMAP. SMAP is an innovative academic system that provides a comprehensive view of the scholarly work. With a vast database containing 220 million papers, 150 million scholars, SMAP has fully discovered the connections and involving features among researchers, papers, and topics in academic data. Our website offers a unique way to explore the academic landscape, allowing users to navigate through a knowledge graph-based interface that visually represents the connections between different scientific concepts and researchers. And welcome to visit our website, smap.info. And I will share my work about temporal knowledge graph reasoning. The contents consist of 5 parts: background, motivation, our proposed method, experiments, and conclusion. First, I will introduce the background of knowledge graph and temporal knowledge graph. In fact, in the real world, there are 3 types of graphs: the normal graph, heterogeneous graph, and knowledge graph. So what's the difference between them? Here are the formal definitions of these 3 types of graphs. A graph is a collection of nodes and edges. For instance, social network and citation networks are all typical graphs. The second definition is a heterogeneous graph, which can also be called heterogeneous information network, HIN. Its main difference from graph is that it has multiple node or relation types. Among them, our SMAP's academic network is a heterogeneous graph. For the third definition, it can be seen that KG is a multi-relational graph composed of entities, relationship types, and facts. The fact can be in form of triples, including a head entity, a type of relationship, and a tail entity. Some people like call them subject entity, predicate, object entity. They are exactly the same. And we can say knowledge graph is a special type of heterogeneous graph, but it focuses on fact-based triples. It should be noted that in knowledge graph, the number and the type of edges between 2 entities are arbitrary. Therefore, from the point of structure, the relationships and the passes between node types in the knowledge graph are exponential level, far exceeding those in other types of graphs. Interestingly, although knowledge graphs belong to heterogeneous graphs, researchers in these 2 directions rarely cite each other's paper. Here is a typical knowledge graph. It includes some well-known entities such as Paris, Mona Lisa, and Eiffel Tower. Now, from the example, we can see that a knowledge graph is a semantic network storing knowledge with nodes and edges. The nodes in a knowledge graph represent entities, while the edges represent relationships between these entities. Just as I have said in the previous slide, Facts are represented as triples, which consist of a head entity, a relation, and a tail entity. For example, the triple Da Vinci painted Mona Lisa represents a fact in this knowledge graph. Recently, research on knowledge graph has mainly been divided into 4 parts: knowledge representation learning, knowledge acquisition, knowledge-aware applications, and a temporal knowledge graph. As a storage model, knowledge graph can effectively solve real-world problems, such as the red box in the upper right part, which includes tasks such as natural language understanding, question answering, dialogue system, and recommendation system. These tasks are widely beneficial for knowledge graph reasoning for many years. Until last year, knowledge graph was replaced by large language models such as GPT-3 and GPT-4. But knowledge graphs can still be used as structured knowledge to improve the interpretability and accuracy of large language models to some extent. Now let's move to temporal knowledge graph. It's a toy example containing 3 snapshots. The fact, also called event, in temporal knowledge graph has extended from a triple, SPO, to a quadruple with a timestamp T, that is SPOT, where S and O denote subject and object entities respectively, and P as a relation type means predicate, same as static KG. There are 2 different settings of TKG reasoning, that is interpolation and extrapolation. As we all know, knowledge graph itself is incomplete. It may lose some important links because humans and automated tools cannot find all the knowledge. As to interpolation, methods are supposed to find those missing facts in the observed temporal information, and interpolation can be taken as knowledge graph completion. For extrapolation, models are designed to predict future events which happen after the given timeline. And this is also what we are concerned about. The second part is the motivation of our work. In fact, many efforts have been made toward modeling the structural and temporal characteristics of TKGs for future event prediction. For example, here are 2 classic TKG event forecasting models, ReNet and ReGCN. ReNet formulates the temporal link prediction in an autoregressive fashion, which utilizes gated recurrent units to capture the spatial temporal dependencies. ReGCN learns the evolutionary representations of entities and relations with graph convolutional network. And it's modeling the KG sequence recurrently. These models make reference to known events in history, which can easily predict repetitive or periodic events. However, in terms of the event-based TKG, such as Integrated Quasi Early Warning System, ICEWS, new events that have never occurred before account for about 40%. Let's see the figure. It shows the frequency or numbers of new events under different timestamps. The x-axis is timestamp and the y-axis is frequency. New events continuously appear across all timestamps. It's challenging to infer these new events because they have fewer temporal interaction traces during the whole timeline. What's more, the figure shows a query which country does the United States negotiate at the time t+1. The answer is Russia, which is a new event. Most existing methods often obtain incorrect results over such a query due to their focus on the high frequent recurring events. Here, the US frequently negotiates with North Korea. Here is the North Korea triple. This making many methods fail. Specifically, during the inference process, these existing methods will rank the probability scores of all candidate entities in the whole graph without any bias. We argue that the bias is necessary when approaching the missing entities of different events. That is, for repetitive or periodic events, models are expected to prioritize a few frequently occurring entities. And for new events, models should pay more attention to entities with less historical interaction. But we don't know which query is related to new events. Therefore, according to the two motivations, we design contrastive event network, abbreviated as SANET for TKG reasoning. I will introduce some notations and definitions, as I think you have noticed some new concepts in this figure. We call the past events associated with the entities in the current query historical events, and others are non-historical events. Their corresponding entities are called historical and non-historical entities, respectively. The following two sets are the historical events and entities. For example, the same query, which country does the United States negotiate at time t+1? Its historical events include negotiate North Korea at t-2, negotiate China at t-1, and negotiate North Korea at time t. Here, North Korea and China are historical entities. Other entities in the vocabulary, including South Korea, Canada, Ukraine, and Russia, are non-historical entities.
Can I ask a question?
Yeah.
How do you select the K? So how far back in the past do you consider the historical events?
I will use the whole timeline to select the historical events.
Okay. Thanks.
Okay. Then we investigate the frequencies of historical entities for the given query Q during data preprocessing. Specifically, we count the frequencies of all entities served as the objects associated with subject S and predicate P before time t. It's shown in the first equation. According to the top right figure, the frequency of China is 1, and the frequency of North Korea is 2, while other entities are 0. Here we can get the frequency vector. Since we cannot count the frequencies of non-historical entities, we scale f to z, where the value of each slot is limited by a hyperparameter lambda. It can also avoid the impact of large frequency of some entities on model performance. Next, SANET learns the dependency from both historical and non-historical events. Inspired by another model called SIGNET, if you know, our model adopts a copy mechanism-based learning strategy to capture different kinds of dependency from two aspects. One is the similarity score vector between query and the set of entities. And it is modeled by a linear layer with an activation function. The other is the query's corresponding frequency information with copy mechanism in the last item. It's the same for the non-historical dependency. In this way, we can use cross entropy loss to train our model for entity classification and obtain a probability of each object entity on the current query. Then let's move to the historical contrastive learning. Contrastive learning are the self-supervised learning paradigm focused on distinguishing instances of different categories. Here is the self-supervised contrastive learning. The middle part of the figure, it's the middle part of the figure. Most methods derive augmented examples, such as image cropping and adding Gaussian noise from a randomly sampled mini batch of n samples, resulting in 2 n samples to optimize the following loss function, given a positive pair of samples Zi and Zj, where Zi is a projection embedding of sample I. Here, tau denotes a temperature parameter, helping the model learn from hard negative samples. According to the contrastive predict coding, minimizing the loss error leads to maximizing a lower bound of mutual information between I and J. Supervised contrastive learning is a type of machine learning technique that aims to learn representations of data by contrasting positive and negative samples in a supervised setting. The goal is to learn a representation function that maps input data to a lower dimensional space, where similar samples are close together and dissimilar samples are far apart. This is achieved by training the model on pairs of positive and negative samples. During training, the model learns to maximize the similarity between positive pairs while minimizing the similarity between negative pairs. This process encourages the model to learn features that are discriminative for distinguishing between positive and negative samples. Supervised contrastive learning has been shown to be effective for various tasks, such as image classification, speech recognition, and natural language processing. And in our paper, we adopted as part of our training framework for event forecasting in temporal knowledge graphs. So how does historical contrastive learning work in our model? And what's the standard of positive and negative pairs? Let's review our motivation. Many repetitive and periodic events are only associated with historical entities. Besides, for new events, existing models are likely to ignore those entities with less historical interaction and predict their own entities that frequently interact with other events. Therefore, the proposed historical contrastive learning trains contrastive representations of queries to identify a small number of highly correlated entities at the query level. In our implementation, we want our model can identify which queries are more dependent on or preferable to their historical entities. Here are 2 examples. The top one is a positive query, since its answer, China, is in its historical entities set, while the bottom query is a negative one, and it is also a new event. We cannot find any clues or traces of its answer, Syria, in its historical entities set. That's why we call it a negative sample. We use contrastive learning framework to train this queries embedding. The figures shows the detail of the process of historical contrastive learning. We can see that it consists of 2 stages. The first stage aims to learn contrastive representations of different queries in a batch. It employs the canonical supervised contrastive loss. We use an MLP to model the query embedding. It fills the features of subject, predicate, and its frequency vector. When the training of the first stage is finished, SciNet feeds the weights of corresponding parameters of the network. Then it feeds the contrastive representations of queries to a linear layer to train a binary classifier to recognize whether the missing object entity of a query queue exists in the set of historical entities. By this means, we can use binary classifier in the inference. The example shows the current query is likely to find the answer from the historical entities set. The algorithm shows an overview training process of our model. As we integrate the supervised contrastive learning in the training stage 1, we simultaneously optimize the two objectives with alpha balance. And we use cross-entropy loss for entity classification and supervised contrastive loss for query embedding training. Then, just as I have mentioned earlier, we freeze the parameters of the whole net except the classification layer and use binary cross-entropy to train a query classifier in the second stage. During the inference process, the predictions are the multiplication of the results of entity and query classification. That is the probability P and the mask vector B. And the latter tells whether the historical set should be paid more attention. Senet will choose the object with the highest probability as the final prediction. We will use the figure to illustrate the inference process. It's the overall architecture of Senet. The left part learns the distribution of entities from both historical and non-historical dependency. The right part illustrates the two stages of historical contrastive learning, which aims to identify highly correlated entities. And the output is a Boolean mask vector. The middle part is the mask-based inference process that combines the distribution learned from the two kinds of dependency and the mask vector to generate the final results. Let's see the experiments. We select 5 benchmark datasets, including 3 event-based TKGs, ICWS18, ICWS14, and GDERT. And there are 2 well-known public KGs, Wiki and Yago. We also provide the rates of new events on different training datasets. We can see that there are a large proportion of new events in event-based TKGs. In terms of all public KGs, the rates of new events are lower than 20%. Predicting these new events is a challenge for many autoregressive models because mining the non-historical dependency is difficult. Senet is compared with 15 up-to-date knowledge graph reasoning models, including static and temporal approaches. We report a widely used static filtered metric to evaluate models' performance. And our proposed Senet outperforms other baselines in most cases in the 3 event-based datasets. Especially the results of his at 1 improve the most in our model. The main reason is that there exists a large proportion of new events without historical entities in event-based datasets. Senet learns the historical and non-historical dependency of new events simultaneously, which mines those unobserved underlying factors. Note that we don't use any information in the validation set for testing, and Senet doesn't see any ground truth information in the test set. As to public KGs, Senet also outperforms the baselines in all metrics on Wiki and Yago. as can be seen, SANET significantly achieves the improvements up to about 25%. This is because the recurrence rates in these two datasets are imbalanced, and our model can easily handle such data thanks to the concurrent learning of historical and non-historical dependency, which can complement each other. We also investigate the effectiveness of the historical, non-historical dependency, loss functions, and the mask-based inference. I will highlight a variant of SANET. The third one, where the contrastive loss was removed. The figure under the table is a visualization of the query embeddings with spherized PCA projection on Yago. We can see that once equipped with contrastive learning, that is the left one, there exists an explicit border between the two kinds of queries. But if we abandon the supervised contrastive loss, the border disappears. There are two unexplored hyperparameters, alpha and lambda in SANET. The hyperparameter alpha aims at balancing the contribution across entropy loss and contrastive loss, and lambda is a scale parameter for frequency. Due to the difference of characteristics between event-based TKGs and public KGs, the hyperparameters leads to different results on these two kinds of datasets. We adjust the values of alpha and lambda respectively to observe the performance change on SANET, on ICWS18 and Yago. And we choose 0.2 for alpha and 2 for lambda on all datasets. But if we set different hyperparameters for each dataset, our model may achieve better results. We also select 3 representative queries with North Korea as subject entity to investigate the predict results of SANET. The first query is North Korea halt negotiations to which country at a time t. It can be observed that the group halt negotiations, the United States, highlighted in the balloon font. It appears most frequently in the past. It is easy for SANET to obtain the correct answer for the reason that the historical dependency has been captured, and the mask-based inference with a binary classifier can reduce the probabilities of non-historical entities, such as Russia and Singapore, which have nothing to do with the relation halt negotiations. As to the second query, North Korea intend to cooperate to which country at a time t. And the group intend to cooperate South Korea with red font only happened once, which is the same for other object entities such as United States and Russia. And not surprisingly, the model can predict correctly. Although the United States and North Korea had the relation intent to cooperate in the past, SANET believes that other relations between the United States and North Korea were more likely to happen. The first case is the best evidence. Thus, the model chose South Korea. For the last query, North Korea expressed a code to which country at a time t. The query has no historical events from the first timestamp 0, but the model also gets the correct results, showing that our model has learned the non-historical dependency. The last part is conclusion and future work. We propose a novel temporal knowledge graph representation learning model, contrastive event network SANET, for event forecasting. Promising future work includes exploring the ability of contrastive learning in knowledge graph, such as finding more reasonable contrastive pairs. Last but not least, there are two observations I want to share. In our paper, we propose a novel model called SANET for event forecasting in temporal knowledge graphs. One of the key insights of our work is that historical information can be more important than the graph structure for event forecasting tasks. By historical information, we mean the frequency with which certain events have occurred in the past. For example, if a particular entity has frequently interacted with another entity in the past, it's more likely that they will interact again in the future to some extent. Anyway, this historical frequency can provide valuable information for predicting future events. In contrast, the graph structure refers to the way that entities and events are connected in the knowledge graph. While graph structure is certainly important for many tasks, we found that it may not always be as important as historical frequency for event forecasting. This insight is reflected in our model design, which uses contrastive learning to learn a convincing distribution of the whole entity set and identify significant entities from both historical and non-historical dependency. And you can find that SANET doesn't adopt any graph structure. Thus, at present, we are trying to use the autoregressive language model to learn the temporal sequence of events. We have designed a set of temporal sequential language and adopted a transformer-based model to train TKG. And we can obtain similar performance as SOTA. Well, that's some observations when I was doing the experiments. Our work is now open source. Welcome to use it for future work. This is the end. Thank you first for your attention. Do you have any questions?
Yeah, thanks for the great presentation. I think Julia, you have a question. Go ahead.
Yes, I have. Thanks for the presentation. I very much like this idea with the contrastive learning. Could you go please back to the slide with this with the figure of the framework and inference? This whole figure.
Okay.
I don't remember the slide number.
The inference process.
So the slide is called Contrastive Event Network Framework and Inference. Yeah, this one exactly.
Yeah. Okay.
I think I'm not sure if I completely understood it. The middle part of the figure. So I understand that in the left part you have the distributions from the historical part and from the non-historical part, and in the right part you do the contrastive learning to kind of learn to differentiate between the defects which are historical and defects which are new. And then if you have a query, your classifier will tell you if this is now a new fact or an old fact somehow. And then based on this, how it was classified, you get the prediction. Is this correct so far?
Yeah, we can generate a probability from historical dependency and non-historical dependency. We can get a distribution here. And for contrastive learning, we will generate a mask vector to see whether the current query is a new event or not. Yeah, then we can combine these together to generate the final results, and it shows in these slides. So here, and the first item is the historical and non-historical dependency distribution, and the last part, the final part is the contrastive Boolean vector. And each slot means whether the current object is in its historical entities or not.
Okay.
Yeah. So we can combine them together to get the final results.
And then could you go back to the figure, please? And then, for example, you have this probability distribution of the non-historical dependency. And then if you kind of decide, or if your model decides that the triple is a new event, it will somehow sample a node from this non-historical dependency. Is this correct? I'm not sure if I understood.
If our classifier predict is a new query, then we can go find those non-historical entities. If it's not a new query, we will find its historical entities.
Okay. Thanks for explaining.
Okay.
It's quite surprising that you don't need the graph properties or structure at all for this. Quite interesting.
Yeah, thank you. Do you have other questions? I think you are doing some knowledge graph research.
Yes. I do have more questions, but if somebody else wants other questions first, that's also totally fine for me.
Yeah, so I'm not too familiar with temporal knowledge graph, but I think it's very interesting that here the graph structure is not used. I think maybe there are still ways to add the graph structure that will improve the performance further, but I'm not sure. Yeah, go ahead.
That's a good point. I think we can we can revise the encoder here, and we can add some graph structure in this encoder to make them more specific, such as we can use GCN or GRU to encode this graph structure and generate some context vector to generate the probability.
Right, or even just the one hop or two hop neighbor of these.
In our implementation, we just use one hop neighbors to find the historical and non-historical dependency.
So it kind of shows that in this task for now, it seemed like one hop is a pretty strong inductive bias. So I guess the performance gain can also be explained that the model are just focusing on the one hop, so it doesn't need to like look too far ahead to make predictions, and it's kind of more more on the time series side that matters than on the complex global graph structure side, I guess.
That's right.
In
our graph structure, in our model design, we indeed don't use the graph structure. We focus on the historical frequency.
And can you go back to the slide where with the data set statistic?
Yes.
So yeah, so it seemed like these are pretty interesting data sets. So for training, that's the number of edges, right? So for the training and validation column, you are showing the number of edges.
Number of edges.
The number of links.
Links here.
Right. So these are also these are relatively small data set in terms of comparing with like OGB size data set and so on, especially considering this is like across time in terms of temporal wise, because like we can expect that real world temporal dependencies are would be like a lot bigger because you have the time aspect and also so have you tried to play with, or do you plan to try with some data set that maybe are of a different order of magnitude bigger than what you currently have here? Do you think that will change the result?
Actually, we use these 5 data sets since they are widely used in other models. And I think our model can scale up to larger graphs since we didn't use any graph structure. So the time complexity is not that high. And I think here the GDLT is a large graph, is a large temporal graph, and we indeed use more time, test more time on these data sets.
Right, that makes sense. Thanks. Yeah, okay. Yeah, thanks for the explanation. Are there any other questions from the audience as well? And also Farman, feel free to ask.
I also have one question. Do you have any discussion on how you selected the negative edges? Because for the positive ones, we saw that there were some relation between the history of the links and the way that we are predicting them. I would like to know whether there was something like that for selecting the negative edges.
I think you want to ask how I select the positive and negative samples.
Yes.
Let me see. Actually, we use the let me see. These negative and the positive samples are all in a batch, and our batch is 1,000. And there and the distribution of different batch are different. So I think we don't use specific negative sampling in our model.
So the dataset contains the negative edges, or?
No. Actually, in our historical entities, we can say it's a positive sample, and for non-historical entities, which is not in the database in the GKG data sets, we say it's a negative sample.
Okay, I see. Thank you.
Okay, thank you.
Okay, sounds good. So if there are no more questions, do you have more questions, Julia?
Yes, I do.
Okay, go ahead.
On the experiment table, could you go to that slide, please? To the table with the results.
Here?
Yes, this one. So I have a question on this sentence. Note that we don't use any information in the validation set for testing. So this means you use all the information from the taint set and then you do the testing, right? And you don't feed the validation information.
We use validation set for model selection, and we don't use any information in the validation set for testing. And the Senate doesn't see any ground truth information in the test set. And I think you so what can you repeat your questions again?
Yes, if you do not use the validation set information during testing, this is what you're saying here.
Yes.
Because I think so most of the other models actually do use this information from the validation set during testing. So I think you could get even higher scores if you would also use that validation information during testing, because then the model has even more information. And I think in this forecasting setup, this is actually allowed.
Yes, you're right. In our original implementation, we didn't make predictions step by step, but directly predict the events based on the information from the training set, which also limits the performance of our model.
Okay. And I have one more question on so you evaluate based on the static filtering, because do you know about
yeah.
Do you know about time-aware filtering, which has been done in some of the more recent temporal knowledge graph extrapolation papers?
Yes. We know that the field setting may not be the most appropriate evaluation metric for temporal link prediction because doesn't consider the time validity of facts. And we have learned, we have also knowledge, we have learned that some papers propose the time aware evaluation, and I think and we agree that there is a need for more comprehensive evaluation metrics for temporal link prediction. But when our work started, we follow another two work called SIGNET and REDENT.
Yes.
If we change to the time aware setting, we will need to modify most of the baseline codes, which may introduce more errors. We also know that using the field settings can still provide some insights into the performance of our models. So we just choose the static field setting.
If you ever compute the results for your method on time-aware filter setting, I would also be very interested in seeing that. If you ever do that in the future.
In our GitHub repo, we have provide the time-aware setting codes.
Ah, great.
Yeah.
Cool.
We will in our following your future work, we will use time-aware settings, and we will not use the static field setting. And that's a good question.
Great, then I will just check out the GitHub repo. Thank you.
Okay.
Sounds good. All right. Let's thank Yishu again for his great talk today and discussion and interesting ideas. So so we'll see you all next week at the same time. And have a nice week, everyone.
Okay. So, thank you, Andy.
Thank you.
Thank you, everyone.
Thank
Goodbye.
you very much.
Bye.